All right, here we go with your shapes. So, and we'll have a look at what's happening here. All right, and I think this is as good as having this section done at this stage, so it will be. Now, again, I have 25 minutes, so I do 50 marks, half the marks. There'll be loads of easy marks in this. All right, there'll be some marks you're going to have to work to get, but you got to understand what's going on. That's going to be the most important part of this question. Shapes in the form of small equilateral triangles can be made using matchsticks of equal length. An equilateral triangle. These shapes can be put together into patterns. The beginning of a sequence of these patterns is shown below. Draw the fourth sequence. Now, there's nothing wrong with drawing these because, like, to draw them out is nice because you get to know what's going on. Just don't draw it too big that it doesn't fit into the thing. What am I doing? Oh, stop. One triangle. And you draw another triangle. And when you draw them, you'll get to learn the dimensions much better than just looking at it, so you will. Right, you're going to get the marks in the leaving cert for doing this. You'll be happy enough to draw it on the day, so you will. I draw it myself if they give me marks for it. I'd love to go and do the leaving cert again now myself. Huh? I reckon I'd pass it this time. Okay, there's some marks for me. I'm going to say thank you very much now for them marks. Right? And it's a great idea to draw it out. And there, I've just had an offer that I can sit one of your papers. Huh? I might go and do that on the day. Huh? So I might. The table below shows the number of small triangles in each pattern and the number of matchsticks needed to create each pattern. The number of small triangles, there was one small triangle. 1, 2, 3, 4 small triangles. 4, 5, 6, 7, 8, 9 small triangles. 10, 11, 12, 13, 14, 15, 16 small triangles. I added on 3 here, yeah, and then I added on 5 there, and I added on 7 there. It looks like it's a quadratic function. That's what it looks like to me, right? And of course, 1 squared, 2 squared, 3 squared, 4 squared. It looks like the number of triangles is the number and the pattern to be squared. That's what it would be. The number of matchsticks, 3 matchsticks. 3 there. Add on 3 and add 3 is 9. You add on 3 there, 3 there, 3 there. Number of matchsticks in the pattern, 3, 3. You added on another 9, which is 18. So you added on 3, twice 3, 3 times 3. So going in here, you added on 3. You added on 6. You added on 9. So it'll have to be 27, right? Just working it out to see what it may just be. Is that okay? Is that right? Hold on. I didn't. I added on 6. 3. Then I added on twice 3 because there was 2 triangles. I beg your pardon. And then I added on 3 times 3. Added on 12. 4 times 3. Yes, do you understand that? Because I added on, to go from there to there, I added 2 triangles. To go from there to there, I added 3 triangles. To go from there to there, I added 1, 2, 3, 4 triangles. Now, you're saying, did I not add that triangle? I did, but that I didn't need matchsticks to make that one, or that one, so I didn't. All right? Of course, we're on 2013 now. Write an expression for the number of triangles. Well, the number of triangles for the nth pattern is n to be squared, right? Find an expression for the number of matchsticks needed to turn the n-1 pattern into the nth pattern. Now, this is going to be a simple answer once we know what's been asked. Find an expression in n for the number of matchsticks needed to turn the n-1 into the nth. So to turn the first pattern into the second, the first into the second, I added twice 3. To turn the second into the third, what happened? To go for the second, I added on 3 triangles. I added on 3 times 3, because there's 3 matchsticks in each triangle. To turn the third pattern into the fourth pattern, I added on that one, that one, that one, and that one. And each of them had 3, was 4 times 3. So to turn the n-1st into the nth pattern, it'll be 3 times, it'll be n times 3. You need 3n matchsticks. And again, I'll always go back to see, can I try and make out what's happening? Any questions about that part? And again, on your day, you're going to have to use your own logical reasoning. You're going to have to know what's going on. The number of matchsticks in the nth pattern can be represented by term n is an squared plus bn. So it's a quadratic sequence. Find the value of a and the value of b. Well, the number of matchsticks in the first pattern, the second pattern, the third pattern, and the fourth pattern. I'm just taking them down from the table because I've it made bigger. The number of matchsticks was 3, 9, 18, and 30. That's the sequence. The first difference was 6. The first difference is 9. The first difference is 12. If the first difference was all the same, it's linear, it's arithmetic. That difference is 3, that difference is 3, that's the second difference. The second difference is a constant. Therefore, this an squared, twice a is 3. So a is 3 over 2. The second difference, half the second difference is always that number. So I know the nth term of this is 3 over 2 n squared plus bn. Okay, so that's the first part of it. I know that number a. I know the first term is 3. Term 1 is 3 over 2 by 1 to be squared plus b times 1. The first term is 3. So 3 over 2 plus b is equal to 3. B is equal to 3 minus 3 over 2. B is also equal to 3 over 2. I've done that right now. 2a is 3 over 2. The first term is 3. So n is 1. 3 times 1 to square is 3. So a is 3 over 2 and b is equal to 3 over 2. And you understand about the second difference, making it a quadratic sequence. So, right? Tricky now because this question is flittering around from bit to bit, so it is. One of the patterns of the sequence has that many matchsticks. How many small triangles are in that pattern? One of the patterns, well, this is the pattern. Term n is equal to 3 over 2 n squared plus 3 over 2 n. And that value, if that's the number of matchsticks that must be in the sequence, then that must equal that 4, 1, 3, 4 multiplied by 2. 3n squared plus 3n is equal to 8, 6, 2, 8. I wonder, could I divide by 3? N squared plus n, 3 will go into 8 twice and 2 over. 3 will go into that 7 times and 1 over. 3 will go into that 5, 6. 2, 7, 5, 6. So n squared plus n minus 2, 7, 5, 6 is equal to 0. There's a quadratic equation I have to solve. I don't know the factors of 2, 7, 5, 6, so I don't. So what I would do is, it can't be a minus b formula because the nth term won't be decimal places. I'll divide 2, 7, 5, 6 by a number, and because this is plus n, there can only be 1 between them. 2, 7, 5, 6, let me divide it by 50. So divided by 50 is 55. There's a gap of 5, so I have to be bigger than 50. 2, 7, 5, 6 divided by 53. There I go. N plus 53 by n minus 52 is equal to 0. So n is minus 53, or n is 52. N equal to 52 would be the solution to that. Alright, so do you understand how I was thinking when I was trying to get it, right? Because I knew n would be an element of the natural numbers because it was a term.